What is the link between roads and the climate crisis? Roads are primarily designed for the transportation of people and goods from one place to another, safely, comfortably, and expeditiously. Roads can be constructed using machines or labor-intensive methods. Labor-intensive methods are where labor using hand tools is the primary resource and is supported by light equipment if necessary, thereby creating more employment. Traditionally, road deterioration is largely influenced by the following variables: road building materials, construction methods, terrain along which the road traverses, traffic in terms of the number of vehicles using the road, and the proportion of heavy vehicles to small ones. One heavy vehicle has the same damaging effect as tens of smaller ones. Maintenance strategies and environmental conditions. Quite often, these variables act in combination. For example, use of substandard construction methods, utilizing poor quality materials in hilly terrain, in a high rainfall area, on a poorly maintained but highly trafficked road with heavy vehicles is a cocktail for disaster. But the most important factor accounting for road failure is water. The effect of water can, to a large extent, be controlled by the drainage that is provided. The climate crisis is manifesting in unpredictable weather patterns, characterized by more frequent and more intense rainfall, including cyclones. This means a lot more water. In March 2019, Tropical Cyclone Idai struck Zimbabwe, Mozambique, and Malawi. Cyclone Idai is recorded as one of the worst tropical cyclones on record to affect Africa and the Southern Hemisphere. In addition to the human casualties, infrastructure, which includes roads, was destroyed. In April 2019, floods damaged infrastructure in South Africa, including houses, roads, and bridges.
I had the opportunity to visit Mozambique, Zimbabwe, and South Africa to do post-disaster assessments of infrastructure that was left damaged. Besides the loss of human life, these disasters left a trail of destruction in terms of damaged infrastructure, including roads and bridges. With bridges, all of them overtopped. The parapets got damaged, the approaches to the bridges, the fill material was eroded away, the superstructure was left standing. If a disaster of similar magnitude is to strike again, we need to be prepared. First, we need to repair the damage. It's not simply putting back what was there. We need to build back better so that if a similar event occurs, we have less damage if we get damage at all. The next thing we need to do is to climate-proof the infrastructure that was not damaged. This means we have to go back and do some retrofitting in terms of improvements so that the existing infrastructure will not be damaged by similar events. It is better to be prepared to know where your infrastructure is than to start looking for it post-disaster. The third thing we need to do, we need to learn from what has been damaged and revisit our design standards.
In the context of adaptation for roads, this may entail introducing better building standards for disaster risk reduction measures, using materials and construction methods that are more locally attuned and responsive to the local environmental conditions.
When man goes into a catchment and fiddles with it in any way, be it overgrazing at the top of the catchment or introduction of agriculture along the catchment, any hard surfacing such as roads or towns and cities, we change the whole dynamics of the flow. So we look at the catchment in its entirety. Nature naturally creates an equilibrium, and where man has intervened, man has broken that equilibrium. And I think the ultimate engineering quest is to try and restore the equilibrium as naturally as possible. Using grass-lined stormwater channels, including in cities, because the grass-lined channels absorb water but also slow it down. look for roots of plants to hold the soil in place, just as Mother Nature intended.
While we're all focusing on drainage and how to control it, I think it's also important in a water-scarce country like South Africa to look at what can we do with this runoff. We control it and we design for it up to a point and then we let go of it. I think part of drainage we also need to see how we can conserve this runoff water and reuse it.
Climate conditions affect the geographic location of some trees, whose occurrence may also be influenced by certain soil properties. Armed with the knowledge of trees, an engineer can identify areas with potential drainage problems in the road design process.
Natural systems perform better than man-made systems in terms of disaster mitigation, which means us as humans, we fit our designs to what the rest of nature is doing.
As we transition to the fourth industrial revolution in a changing climate, it is imperative to leverage knowledge, tools, and resources across non-traditional partners. Who knows? Maybe one day we will build roads that perform better the more flooded they become.